So for the last lecture of this week, let's look at some more higher order functions which are built into Haskell for lists. The first function is called take while, and it is a variation on the function take which we have seen. So remember that if we give the argument n and l to take, then it uses n as the number of elements to extract from it. So take n l returns a prefix of l with n elements. Now sometimes you may not want to take a prefix according to a fixed number but according to some property, and that's precisely what take while does. So here is an example, here is a type of take while. It takes a property, okay, so it gives a function from a to bool like a filter function, and then given a list of a, it takes the longest prefix of the list which satisfies this property. So here is an example. So here the property is greater than 7. Okay, so as long as the number is greater than 7, the property is true. So if you take this list, then this number 8 satisfies the property, but 1 does not. And so even though 9 and 10 satisfy the property, the take stops here. So take while of this property greater than 7 for this list gives the list 8. Notice that if you had done filter, you would also got 9 and 10. So this just goes up to the first point where the property fails and gives you the list before that. So analogously, if you change the property for this list and ask for all the numbers which are less than 10, then it finds that 8, 1 and 9 are all okay. But on the other hand, 10 itself is not strictly less than 10, so you get 8, 1, 9. So as an example of using this, let's look at a function we have seen before. So remember that the function position takes a character and a string and returns the first position in the string where C occurs. And of course, if C does not occur in the string, then we get a position equal to the length of the string, which is technically outside the string. So we had given this inductive definition earlier, where we have the base case of the empty string. And if it is not empty, we check the first character, and otherwise we inductively add 1 to the result of finding the character in the suffix or in the tail. So if we use take while, we can write the same function in a very succinct way. So what we check is, what is the first character in S which is not equal to C? Right? So if all the characters in S are not equal to C, then this will give us the entire string back. Otherwise, it will give us a number of characters before the first C, and that is precisely the position of the first C. Right? So position of C is just take while not equal to C of S, and then take the length of the resulting list. So remember that take had a symmetric function drop, which instead of extracting the first elements, removed the first 10 elements and gave us a remaining suffix. So analogously, there is a drop while, like take while, which will drop the prefix which matches the pattern, and starting from the first position which does not match the pattern, it will give us the rest of the list. The next new function that we look at is called zip with. So recall the function map. So what map does is it takes a list, say x0 to xn minus 1, and then it takes a function, and then it produces the list fx0 to fx minus 1. Right? So it takes one list and produces another list. Now what zip with does is that it takes two lists and combines them. So I have a list L1, I have a list L2, and now what it does is it takes a function which combines these two values and gives me a new value. So here is an example. If I have two lists 1, 2, 3 and 7, 8, 6, and I have the function plus, then it will combine element by element. So it will say 1 plus 7 is 8, and then it will say 2 plus 8 is 10, and then it will say 3 plus 6 is 9. Right? So it gives us element by element. It position by position, it evaluates this function on the corresponding elements in the two lists. Now if the lists are of unequal length, then it will stop when the shorter list runs out. Right? So here we have 3 elements in the first list but only 2 here, so there is no matching value for this, and therefore the final thing has only 2 elements in it. As a final example, let's look at this function less than. So here it, for instance, compares 1 with 2. So since 1 is less than 2, I get true, and on the other hand, since 2 is not less than 1, I get false. So the type of zip with is that In these functions, we saw here that we had a function plus which takes two ints and returns an int. We had less which takes two ints and returns a bool, but in general the function could operate on two different lists of two different types. So I could start with a list of A and a list of B, and I have a function which takes these two arguments and produces a list C as the output. So in general I have a function which takes two arguments of different types and produces a third type, and it takes as input a list of the first type, a list of the second type, and produces as output a list of the third type. So the type of zip width is A to B to C, to list of A, to list of B, to list of C. So let's look at an example that uses zip width. So suppose we have a list of lists corresponding to marks of students in some assignments in the class. So each list inside, each inner list, okay, looks like, so these are the marks of assignment 1, these are the marks of assignment 2, and so on. So this is for student 1, this is also for student 1, this is for student 1, student 2, student 2, student 2, and so on. Right? So we have a list of lists. Inside we have the marks of each student in a given assignment in one list and a list of such lists. And now what we want to do is combine the marks of each student and get a total. So we want to say that student 1 got 10 plus 9 plus 8, okay, which is 27. And then we want to say that student 2 got 10 plus 2 plus 2, which is 14. And finally that student 3 got 8 plus 10 plus 8, which is 26. Right? So we want to write this function add marks, which will take as input this list of lists and produce a list of int of the same length as the inner list. Now as before, we could have inner lists which are not of the same length, so we will just take the minimum length which occurs across all. So if we want to add the marks where the first list has 2 elements and the second list has 1 element, so since there is no matching thing for this 4, we will only get one output, which is 3 plus 2 is 5. So we can use zip width in the following way. Assume that, so for the base case, of course, if we have just one list inside, then that is the final list. So if there's only one assignment, then the total for each student is the marks in that assignment. On the other hand, if we have multiple assignments, then inductively we assume that we have computed the sum for the remaining part. Okay, so we have done add marks of the tail, and now we want to combine the marks for the first assignment. So we want to do it element by element. So this is a natural situation where we can use zip width. Okay, and zip width will just add element by element the marks in the first assignment with the cumulative marks in the remaining assignment. So this is an inductive definition, when in the inductive step we use zip width. Now notice that this zip width is basically doing this plus across this entire thing. So this is very much like the sum of a list, except it is a different type of sum because we are taking element-wise sums of the elements. So just as sum could be expressed using the fold function, here also we can make this whole definition much more succinct by saying that add marks of a list is the same as folding zip width plus, but using fold R1, because if we have no marks, if we have an empty list of marks, then we don't want to give any sensible output. So therefore, assuming we have at least one assignment with marks, then we can start from the right and fold this function through the list. Notice again that we have used this currying style. So what this says is that if in any context, if I have L here and L here, then the reduction will first replace add marks by this definition. So a simpler form of zip width is called zip. So zip doesn't apply a function, it merely combines two lists into a list of pairs. So it takes a list of A's and a list of B's, and then it pairs them up as the first A with the first B, the second A with the second B, and so on. So zip takes a list of A, a list of B, and gives me a list of pairs of the form A comma B. So as with the earlier function, zip also stops with the shorter of the two lists. So if it can't form a pair, then it stops. So for instance, if I take a list consisting of 3 letters A, B, C and 3 numbers 1, 2, 3, then I get the pair A1, B2 and then C3. On the other hand, if I ask for the zip of A to Z, which has 26 elements, with a list 1 to 10 which has 10 elements, then I only get a 10 element output, because once I reach j in the first list, I find that there is no pair for k because we have run out of elements in the second list. Right? So zip will stop with the shorter of the two lists. So let's look at ways to use zip. Remember that we wrote functions of this type right at the beginning when we were looking at lists. So non-decreasing says that a list is basically going up, right? At any point, either it stays equal or it goes up. Non-decreasing takes a list of int and returns a Boolean value, which says that the list never has a situation where the value goes down. So the base cases are that if the list has 0 or 1 values, it is always non-decreasing. And if it is 2 values or more, then we just check the first pair of values is non-decreasing, that the second value is at least as big as the first. And inductively, we check that the tail of the list is non-decreasing. So this is our standard inductive way of defining this function. So how would we use zip for this function? So effectively notice that what we are doing is we are checking whether x1 is less than or equal to x2, and then x2 is less than or equal to x3, and x3 is less than or equal to x4, and so on. So I can imagine that if I write x1 to xn minus 1 and x2 to xn, then we are checking pairwise at each position that this holds. Right? So this gives us a suggestion that we might want to construct these pairs and then look at the value of less than on each of these pairs. So we can pair up a list with its tail and compare position by position. Now we take a list and we pair it up with its tail, then we have x1 to xn, and on the bottom we have x2 to xn minus 1, and because zip will take the shorter of the two lists, basically xn will get eliminated, this will also be xn, but basically in the second list we have one less value, and so xn minus 1 on the top will get paired up with xn below, but the last xn on the top will go away. So when we do zip L and tail of L, we will get pairs of the form x1, x2, x2, x3, x3, x4, and so on up to xn minus 1, xn. Right? So we take all such pairs, and for each pair in this zip, we check that x is less than or equal to y, and then we apply this AND function. Okay, so this AND function is a function which is predefined in Haskell, just like sum and so on. So what AND does is it checks whether a list of booleans is all true. Okay? So AND of b0 to bn minus 1 is b0 and b1 and b2 and bn minus 1. Right? So AND is just a function which combines all the elements in the list with AND. So these are called booleans. Each boolean is generated by a pairwise comparison of two adjacent elements, and these adjacent elements are constructed by zipping a list with its tail. So a second example of the use of zip is the function position. So remember, we already saw in this lecture a new way of writing position using take while. Now we will see a new way of writing position using zip. So what does position do? Remember that position returns the first position in the string S where the character C occurs. So the strategy to use zip is to first associate with each character its position. Right? So we zip S with the list 0 to length of S. Now technically we want length of S minus 1, but again, since zip will throw away the last value, which is useless, the positions in S are from 0 to length of S minus 1. Right? So since the last position will get thrown away, it doesn't matter, and this is more succinct. So technically 0 to length S has one more position than we need, but zip will take care of it. So we first construct this list. So now we have, if we had a string like hello, okay, then now we have a string which says like H0 E1 up to O4. Okay, so this is what we have got now. Instead of a list of characters, we have a list of pairs of characters and positions from 0 to n minus 1. Now, in this list, right, of pairs, we want to find all of those positions where actually we have the letter we are looking for. So we are looking for a C. Okay, so we check all pairs y comma I where C equal to y and extract only the indices. Now, because this will go through in the sequence 0 to n minus 1, these indices will be in ascending order. Right? So the first element of this list will be the first position where C occurs. Now the only problem is that if C does not occur, then this list will be empty. So we have to take care of that. So we basically want to take the head of this list. We want to take the head of this all pos CS, because that is the list of positions where C occurs. But unfortunately, there may be a situation where C doesn't occur, in which case we have an empty list, and head first of all will not work on the empty list, and secondly it will not be the answer we want, because position CS is supposed to return length of S in case there is no position where C occurs. But this is easy to solve. What we do is we add this position length of S to the end of this list. So if this list happens to be empty, right, if the list of all pos is empty, then the result of this plus plus will just be the list containing the number length of S. So then head of that will return correctly length of S. On the other hand, if there is at least one position where C occurs, then that will produce an element to the left of length of S, and head will return the first such position. Okay? So this is another way of doing position. So we saw one using take while, and now we have seen one using zip, where we associate with each character in the string its position, and then we scan these positions and extract all the positions where C occurs. So let's look at some more interesting functions on lists just to get some practice with programming. So the first function is something which computes the prefixes. Let us call it initial segments. So what are the prefixes of a list? So the prefixes of a list are all the lists which build up the list. So the first prefix is always the empty list. Then we can have the prefix up to 1, which is the list 1. Then we can have the prefix up to 2, which is the list 1, 2. And finally the list itself, which is 1, 2, 3. Right? So these are all the initial segments. Right? So starting from the beginning, stopping at before position 0, before position 1, before position 2, and so on, up to taking the entire list. So we want to compute the initial segments of the list. So of course the initial segments of the empty list was easy. The initial segment, the only initial segment an empty list has is the empty list itself. So the base case is easy, right? So this is easy. Now what happens when we have the initial segments of a non-empty list? So supposing I take a list like this, right? So let us take a simpler one. So the initial segments of 1, 2 is going to be empty, 1 and 1, 2. Okay. Now what are the initial segments of, say, 0, 1, 2? So notice that every initial segment of 0, 1, 2 will consist of 0 followed by a segment over 2. So I will have 0, 1, I'll have 0, 1, 2, I'll have 0, this, and I'll have to now generate fresh an initial segment empty. Right? So this is the inductive thing. It says that the initial segments of x colon xs is first you take all the initial segments of the tail and you add an x in front of them. So you map x dot. So this is the function. So this is a function like our plus 2. Right? So this is a function where we have this operator colon and we have one value fixed. So this will associate with every list an initial x. So this takes all the segments I've already constructed for the tail and sticks the x in front of it. And then I need to, so this is now a list of lists, and then I need to add in front of that a new empty list, because the empty list which was there in the initial segments of x's now has x in it. So I add this. Right? So this creates this, the final step of adding an empty list in front creates this one. Right? So this is how we construct the initial segments of a list. We take the initial segments of the tail, map the head onto each of them, and then add a new empty list up front. So here is another function that we can exercise in programming. So we want to insert a value into a list L at all possible positions and return the resulting list of lists. So it's easier to explain this with an example. So supposing I want to interleave 1 into the list 2, 3, then the 1 can go in position here, so which results in 1, 2, 3, or it can go between the 2 and the 3, which results in the list 2, 1, 3, or it can go after the 3, which results in the list 2, 3, 1. So what we want to do in general is, given a value and given a list, we want to return all the lists that we get by inserting this in appropriate positions. So once again we do this by induction. So if the second list is second argument is the empty list, then the only thing that we can do is to insert x in the into the empty list and create only one output list which contains the value x. On the other hand, if we have to interleave x into a list containing at least one element, then the first thing is to just stick the list, the new value in front of the whole list. So I first have this interleaving where I put the new value x at the beginning. And if x is not at the beginning, then it's inside. But if it is inside, then what is at the beginning is the head of the existing list. So in all these, the head of this list 2 is the one that comes out. So we take the 2 out and then we inductively interleave x in the tail, and for each of those we stick the 2 back in front. Right? So this is as good as saying that I have now done interleave 1 and 3, which gives me 1, 3 and 3, 1. Right? And for each of these I put a 2 in front, and that I get 2, 1, 3 and I get 2, 3, 1. Right? So inductively we interleave x in the tail, and then we put the head of the second argument before each of them to construct all the remaining interleavings. So as our final example, let us look at how to generate all permutations of a given list. So for example, if our list was 1, 2, 3, then the permutations are 1, 2, 3, 2, 1, 3, 2, 3, 1, 1, 3, 2, 3, 1, 2, 3, 2, 1. So this is in no particular order. So we just want to write a function which does it in any order, but obviously some orders will be more systematically easy to generate than others. So first of all, let's understand the type of permutation. It takes a list and it produces a list of lists, because each of the inner things is a permutation, right? So each of these is a permutation, and I have a list of such things. So if I have only one value, so first of all, it makes no sense to ask for the permutations of the empty list. So I'll only deal with non-empty lists. So if I have only one value in my list, then there is only one permutation possible, which is that list itself. Now, if I have multiple values in the list, okay, then the claim is that what I need to do is take 2, 3, the tail, okay, and generate its permutations. So its permutations are 2, 3 and 3, 2 in this case. And then I want to take my new value and insert it everywhere. So I have 1, 2, 3, 2, 1, 3, 2, 3, 1, 1, 3, 2, 3, 1, 2, 3, 2, 1. Right? So what I want to do is I want to take the permutations of the tail and then interleave this head into each of these permutations. This is the function we wrote before, right? It puts x in every possible position in each of these lists, right? And that is achieved by map. So map says interleave x into each of these lists. And now finally, this will result in one extra set of brackets, and so we want to do a concat. So it turns out that this combination of doing mapping a function and then concatenating is actually a fairly frequently used concept in Haskell functions. So there is actually a built-in function called concat map, which takes a function in a list and it does a map of that function through the list and then concats. So the next example is to compute all partitions of a list. So what is a partition? A partition just says that if I take a list and then if I just break it up so that each of these sections is non-empty, then that is a partition. Right? So I need to have a collection of non-empty lists. See, the reason is non-empty is if we have empty partitions, then there's no unique, because I can say that there are 3 empty partitions between here and there, or 1 empty partition, or 0 empty partitions. Then I won't have a finite representation of all the partitions. Whereas if I insist that each of the partitions are non-empty, then there is only each partition can be represented in a unique way. So I want to partition L into L1 to Lk such that L is the same as L1 concatenated with L2 concatenated with L3 up to Lk. Okay, so if we take 1, 2, 3, then the first way we can partition it is to put 2 partitions. I get the corresponding partitions are the list 1, the list 2, the list 3. Or I can put a partition here, in which case I get 1, 2 and 3. Or I can put a partition here, in which case I get 1 and 2, 3. And finally, I can put no partitions, right? So if I put no partitions, I just get a single partition containing the whole list. So again, let's look at the type. So we can examine the type. So each partition is a list of lists, right? So this is, each partition is already a list of lists, right? So this is one partition, it's a list of lists. This is another partition, this is a list of lists. So each partition is of the type list of A. And we have a list of such partitions, so we have three brackets. We have a list of partitions, each partition is a list of lists. So the partition, the only way I can partition an empty list is to take all of it, because I can't put a non-empty partition on either side. Now, if I have a non-empty list, right, then what I will do is I will take all the partitions of the tail. So for instance, if I have 1, 2, 3, then I will take the partitions of 2, 3. So how can I partition 2, 3? Well, I can put it as 2, 3 or 2, 3. There's only one way I can non-trivially partition it, which is to put it in the beginning. Now, how can I partition the whole list? Well, one way is to put one along with this as a new partition, right? And the other way is to attach this to each of the partitions. So basically, if I take each partition here, right, then I can attach X to the first partition, right? Or I can put it separately. So for each of these partitions, either I can do this or I can do 1, 2, 3. Likewise here, I can say 1 and then 2, 3, or I can say 1, 2, 3. Right? So for each partition that I can get out of the tail, right, I can either attach X into it, the first element, or I can take the entire partition and then I can just add X separately as a new partition. That's what this is doing. Right? So this is the first case, is this one, where I actually include the value X into the first partition that I've generated in the tail. Or I have the case where I create a separate partition for X, and that is what is happening here, right? Where I take the partitions that I've already got and I put a separate partition with X. So what we have seen is that we have three new higher order functions that we can use with lists: take, while, zip with, and zip. And using these, we have seen several examples of functions that we can write on lists, including some functions that we have already written without these new things. So a concluding remark about programming in Haskell or in any other language. So programming language is in the end a language. So like languages that we speak, natural languages, in a programming language we can always say the same thing in many different ways, and this is what we have been stressing so far, that there are many different ways to write the same function in Haskell. So initially we use a language in its most direct form, right? We use simple words, we write functions inductively and directly, and this is what is easy to grasp as a beginner. But as we go along and we encounter these new functions, we find that we can use higher order functions like folder and map and zip and list comprehension to compress inductive definitions into more compact representations. Now, there are two advantages to this. One is that the compact representation is often easier to understand. Now, the inductive definition is not difficult to understand, but it is easy to make mistakes, and one has to check that you have written base case and the inductive case correctly without making any typing mistakes or messing up things. So very often the compressed version using these higher order functions is much easier to understand. So it becomes a more effective use of the language. So you should try as far as possible to express your concepts in the simplest form. Of course, sometimes it can be unbearably terse and very difficult to parse. So you should have a balance between writing things out explicitly and using these higher order functions to compress the definitions. But in the end, like in any other language, okay, you must speak it to learn it. So you cannot learn programming without writing programs. So go out and program.